presenter is GEORGIOS. GEORGIOS is a student at the National Technical University of Athens, a decorated competitor in mathematical Olympiads. He was part of the Greek national math team for many years, with most notable award the gold medal in the International Mathematical Olympiad of 2023 in Japan, and with the highest ever Greek score of 35 out of 42. And he will present probabilistic methods in Olympiad combinatorics. So, stage is yours.
Thank you. Well, good morning everyone. My name is TZACHRISTAS. I'm a student at the National University of Athens, and today we are going to talk about the probabilistic method in combinatorics. As we do in music, when we want to study one of the greatest musicians, like Beethoven, we do not have time to study all of the music that he has done. So what I have tried to do here is I have gathered four very nice problems that illustrate this method. Because there are so many that I cannot do a whole presentation, like 2-hour or 3-hour presentation here. Of course, this presentation is part of a longer PDF that I have prepared and that I will publish, and I can also share with any of you if you want. But due to limited time, I am going to show only these problems. So I suppose that many of us know what probabilities are, but the interesting thing is how they connect to Olympiad mathematics. As a former competitor myself, when I went to conferences, I always wanted to see a presentation about maths that are for young people and not only for researchers. So this was very interesting to me, and this is what I'm doing today. So probabilities appear in many areas of our life. Either it is games of chance like the casino, where some people take advantage of their strong mind to make some cash. In medicine, of course, I had seen a very nice presentation about how they expect the COVID outburst to come based on probabilities, and of course there are many other applications like weather forecasting. So we know that probabilities is a very useful tool. As far as the IMO, because the presentation is about probabilistic method in Olympiads, the IMO is the International Mathematical Olympiad. It has been hosted in different countries every year all over the world for the last 67 years, I think. Very long history. Every year around 600 and over 100 countries compete in this competition, and they send up to 6 students. These are some statistics about the points of the competitors, the basics for the medals, and now we are going to dive into the first problem. I have included some one easier, and I'm going to increase the difficulty as we go on. So for this problem, I'm going to need 6 volunteers from the audience. If you are kind enough to raise your hand, I'm not asking for. It's going to be very easy. I'm not asking for thought. Just to play this game. Okay, 1, 2, 3. I need 3 more. 4, 5, 6. Okay. So please raise your hands. So what we want to do is that we take 6 random people, and we want to show that there are either 3 that know each other or 3 that do not know each other. So, who are you, like part of the same group maybe? You know, I know that you know each other, and I do not know about. Okay, so I can find the sir with a t-shirt behind, the boy with a t-shirt here, and my brother John. You 3 do not know each other, right? So we found 3 people that do not know each other. So this is a very classical example, and it can be solved. The most famous proof is with the pigeonhole principle. So, for example, if I take John, John has 5 other people here that he has either connection to or not. So from you 5, he either knows 3 or he does not know 3. For example, John, I think, does not know me here, the sir in the back, and the boy. And now we go to you 3. If 2 of you do not know each other, then you form a not knowing triangle with John. And if all of you know each other, then you form a knowing triangle U3. This is the pigeonhole proof. It is the best one, the most simple, and it's a very good introductory problem to young students who are going to competitions and combinatorics. But I have included also the probabilistic solution to this problem, which is a bit more advanced, so to say. So we want to count the number of triangles we have. From U6, we can construct 6 to 3, which is 20 possible triangles. And because for each person, he has, as we said, 5 other persons he has or has not relation to. So we have that he knows R and he doesn't know B of the persons. The sum is 5. This here, the inequality is very trivial. I will not go into details, and this is what you will see in the whole presentation. I'm trying to keep details out as much as possible. And so we have at least 24 monochromatic angles, and the total number of triangles is 20. So the important thing here, and the probabilistic intuition comes here. We have 20 triangles and 24 monochromatic angles, and each angle belongs only to one triangle. So from these triangles, the average is 24 divided by 2, which is 1.2, I think, which is greater than 1, which means that if the average is 1.2, and all of these are integers, at least one triangle has value 2 or more, which means that if a triangle has 2 monochromatic angles, then we have a monochromatic triangle. This was the introduction problem, and now we're going to see a problem from the International Mathematics Competition of 2002. This is the competition for university students, and in university student competitions we see probabilities a lot more than in secondary school competitions. So we have 200 students. We participated in a contest with 6 problems. And the only thing that we know, which is different from many competitions, is that each problem was solved by at least 120 students. We want to prove that there exist 2 contestants, so that every problem was solved by at least one of them. So for example, we see here, contestant A solves problem 1, problem 2, problem 4, problem 6. Contestant B solves problem 2, problem 3, 5, and 6. So we know that if we make the contestants to write in teams, this team would get a perfect score, right? They would solve all the problems because they would divide them, and then each one would solve the problem that he can. So this, without probabilities, is a very difficult problem. And the key about probabilities is that they come in handy when you have very intriguing and difficult definitions. When we see a combinatorics problem that is very difficult to solve with new definitions, then we'll probably use probabilities. So what we're going to do is we're going to take a specific problem for every problem I. We say that EI is an event that neither of the chosen contestants have solved it. And we want to prove that this cannot happen for every problem, because if every problem was not solved by every, we want to prove that 2 students solved every problem. So the probability that this happens for a problem is the number of pairs of students we have divided by the number of pairs of students that did not solve it, which is at most 80, because we know that 120 people solved it. So at most 80 did not solve the problem, divided by the total number of pairs of students. And now, due to linearity of expectation, we multiply by 6 because we have 6 problems. So the probability is less than 1, which means that there exists a problem, there exists a pair of students who solve all of them. And the interesting thing about probabilities is that most of the time we think that probabilities answer to questions like how probable is this to happen, or which are the scenarios that can happen, which are questions that we do not know exactly the answer to. The very interesting part is that in the problems, probabilities answer with certainty, which is very rare. They answer with certainty that there is a pair of students that have solved all the problem. They do not know which pair it was. They do not know if there was a boy, a girl, 2 girls, 2 boys, nothing. They only know that somewhere there exists. These are the existence proofs and the core of probabilistic method in combinatorics. So now we get to the next example. We want to show that, so the problem is this. We have the numbers from 1 to 1987, and this is a problem from the IMO short list of 1987. Thus the last number is 1987, as you might imagine. And we want to color the numbers from 1 to 1987 with 4 colors. We want to show that if anyone colors them, in whichever way they color them, we can find an arithmetic progression of 10 terms, of length 10, that is monochromatic, that has the same, that the numbers have the same color. And this will happen if anyone colors them, not if I specifically color them in a specific way. Anyone colors them, this will happen. So, first we are going to count how many arithmetic progressions of length 10 there are from number 1 to 1987. We know that arithmetic progressions are characterized by their difference and the first term. If we know the first term and the difference, then we know the infinite sequence of arithmetic progressions that is going to happen. Here, if the first term is A, the second term will be A plus D, D is the difference, A plus 2D, A plus 3D, etc. etc. We want only, though, to count the 10-term arithmetic progressions, because we have limited space up to 1987. So this is the way to count. It is the sum for difference from 1 to 220 of this number. This number is, this would be the upper bound for the first term, because it will have difference D, and the last number would be A plus 9D. We want this to be positive, and we sum over all the possible differences. And the difference, the maximum difference is 220. This comes from this inequality in point 2 as well. So this is the total number of arithmetic progressions of 10 terms. Okay? This is how to say. In competitions, we call it, we need to have some, how to say, technique. These are small details that matter in solutions, but it's not the whole solution. Without this, you cannot solve it, but this is not the main argument. These are called technique arguments, and it's very important that you write all of them, in spite not being the main, thought for the solution. Now we're going to count the probability that an arithmetic progression is monochromatic. So we have the first term, and then for each term, the first term can have 4 different colors, right? So each of the next terms, we can do it. We can count from the first term. The probability. First we choose a color. We have 4 ways, and then for each term, the probability that this term has the color that we have already selected, it's 1 over 4. So we multiply, and the probability is 4 times 1 over 4 to the power of 10. And now, if we get the average is less than 1, which is interesting, which means that not all of them can be not monochromatic, so we can find a monochromatic. And this is with certainty, and this is the interesting part. We use probabilities, which are about uncertainty, to answer things with certainty. So, since the expected number of paths, so to say, arithmetic progressions, the expected number, this is smaller than this. We said that these are the possible, and this is the probability. Is less than 1, then we have 1 monochromatic, at least. We do not know which is, we do not know the first number, we do not know the difference, we do not know everything. We do not know the color it has. We just know that somewhere there is an arithmetic progression of 10 terms that is monochromatic. Of course, there are other problems that can be solved with a probabilistic method that initially appear to have nothing to do with probabilities, right? This, for me, when I first tried to solve it due to in my preparation, I thought that this was an algebra problem. Indeed, it can be solved with algebra and with advanced techniques, but probabilities show us a very, very interesting way to solve this problem, which I'm not going to analyze here due to limited time, but this is, of course, included in the longer version, in the PDF, and as well as many other problems. So, now we're going to the last problem, which is my favorite problem of all time. If you can imagine, someone may ask, what are the probabilities of this? Well, I don't know, but it happened. So I was competing in many years in competitions, and in my last year in high school I went to the IMO in Japan in 2023, as Yannis said. And to be honest, before this competition I was not a believer in probabilistic method in combinatorics. I had studied that there may be some usages of this probabilistic method, but I was, not giving it too much attention. I thought that, no, this is not very interesting, this cannot, what is the probability that I'm going to need this? So I knew like what the definition of a random variable is, but I did not know anything other than that. So it's very interesting for me that I do this presentation like 3 years later, because I didn't know that this was going ever to be useful to me, and it happened in the most important problem in my life in competition. This is problem 5 of the IMO of 2023. It's the last problem I solved that got me to 35 out of 42. The most difficult problem I have ever solved, and to be honest, in the competition, the solution that I gave was not exactly with the probabilistic method, but the intuition behind it is exactly that, and we are going to see it. So the problem was like this. We have a triangle of length n, and we have 1 ball, 2 balls, 3 balls, 4 balls, etc. This is like Pascal's triangle, but not with numbers on it, only the balls. And in each row, if you can see, there is exactly one red ball. Here, exactly one. The figures here are from the official solution. There is exactly one red circle in every line. So the problem is to determine the largest integer k, such that for any such coloring, maybe instead of putting the red ball here, I can put it here. And instead of putting the red ball here, I can put it here. As you can imagine, the number of different colors is very large. With a small, like a string, it can be approximated by mi factorial, because in every row you have 1 space, 2 spaces, 3 spaces, and you multiply. Well, you can, argue that symmetry is a part of the problem as well, but in general is something around mi factorial, which is very, very large. We want to prove that in all of these colorings, this integer k, we want to find the maximum, the largest integer k, such that we can find a ninja path that has k red balls. So a ninja path, what is a ninja path? A ninja path, do we have, a ninja path is, okay, let's follow the mouse. A ninja path is a path that gets exactly 1 ball from each line, and the balls have to be adjacent. So from here, I go to here, I go here, here. I choose in every step, I choose right or left, and I extend my path. So this is an ninja path. Okay, so we construct this graph. And what is this graph? The graph we are going to construct is, for every red circle, we are going to take 2 edges to both of the circles below it, as you can see. And from every from every white circle, we are going to take an edge that is showing not to the side that there is the red circle in this line, but to the other side. For example, in the 3rd row, these 2 white circles have the red circle to the right. So we are going to choose left edges. In the 4th row, these 2 white circles have the red circle to their left. So they are going to go to the right, and this white circle has, this white circle has the red circle to the right, so it's going to the left. And this is the diagram we are constructing. And what we are going to say is this. We have extended, the problem asks for me, and we have added one last row, imagined row, so that we can count the paths we want. We choose a random directed path P by splitting equally only at red circles. So we begin at a circle, and each time we have a red circle, we have to make a decision, right? Because as you can see in the graph, the red circles have 2 edges. So we can make a decision, and if an ninja path that goes to the end has RP red circles, then we have made RP decisions, and each decision has 2 outcomes. So the average, the number of red circles, then the probability of its, how to say, the number of red circles in its path has the probability would be 2 to the minus this number of red circles. And we know that since all of the paths are going to be taken, this by, I do not know the word in English, but all the probabilities must sum up to 1, because this includes every possible scenario. We cannot have a coin that has 1.5 probability to be heads and 1/3 probability to be tails, because where goes the other, what is it? 1 minus 1/2 minus 1/3. All the probabilities must sum to 1, and this is a basic argument in the probability itself. So if we say that every path has at most t red circles, which t is the number we want to find the upper bound for this. So if it has at most t minus 1, then we get this inequality here, which means, and for t equals to k to this number, if we solve this, this is the only inequality that we solve, we get this number, and this is the solution. I will not bother with the details. The last thing that I want to show you is that while this is the most in core probabilistic solution that exists for this problem, or that I know of course, my solution, which is also the official solution of the competition, is the one in the right-hand picture, which is in every circle you put a number, which is the maximum number of red circles that the path that ends to the specific circle has. For example, here in the fourth row here, we have 3, because we can construct a path from here to here to here to here, which has 3 red circles in the path. Here it has 2, because we cannot construct a path that ends here and has, where's the mouse? Sorry. We cannot construct a path that ends here and has 3 circles, but we can construct a path that ends here and has 2 circles. And this was the solution of the competition. But the argument in the end is that the average that you take is larger than the quantity you want, and this comes down again to expectation, which is in itself a probabilistic argument. Sorry for taking everything, talking so quickly and getting over this so very fast. It was a very big struggle for me to choose only that many problems from this very interesting method. I hope you liked it. I hope 1 or 2 things may have stayed with you, and I'm open to questions.
Thank you very much. Are there any questions? Yes, please.
This is a very exciting talk. Thank you. My real question is, when solving such beautiful problems, do you think further on to generalize them, to investigate special cases? Do you make them a research topic?
Okay, I think that is a very interesting question, not only to ask me, but more experienced researchers as well, maybe my brother and many of you. I think that Erdos, for example, has done great work in problems like this, very much. You know it better than I do. There are many problems that in which the opposite happens. We have some research problem which has a small, very beautiful idea, which then introduces a new problem maybe in a competition. In my experience, I have not seen a problem that the other way around, but I think that with the vast majority of problems now being generated similarly with AI, and a very big amount of problems that are going to be generated, I think that maybe in the future this could be a whole new project. Like there would be a team that takes all the problems and expands them, or uses them to solve real problems in society, which, as I have understood in university, is maybe even more important than silly, not silly, I do not dare to say silly, but you know, competitions that are very, very nourishing for the kids, and for me, they have been. But solving real problems in society is more important, and this is why we are here. Thanks.
Very interesting talk. Thank you very much, Georgios. Last but not least, I'd like to invite Albena Vasileva from the Bulgarian Academy of Sciences to present developing computational thinking and achieving educational goals in the context of mathematical competition. Stay safe. Thank you.